Okay, we are live, we are recording, audio and video is up. Lecture 28 in structural analysis. Man, we are moving along. We are continuing our discussion of influence lines. We're going to ratchet it up a little bit today. We're going to extend our discussion past influence lines for just support reactions, and instead we're going to look at influence lines for some internal response, namely shear and moment. Similar pattern with the homework. I'll have a homework for you today due on Friday. And on Friday, what we're going to do is we're going to sort of close out the first part of influence lines, which is just constructing them. On Friday, I want to cover fixed supports, and I want to cover influence lines for trusses. And what we'll do next week is we'll have a couple of days on applications of influence lines. So how do you use them to perform structural analysis? How does the engineer perform them or use them in the aspect of design? So let's recap a couple of things. So first off, let's make sure we're all clear on the fundamental definition of an influence line. It's a graph of a response when you take a unit load and you move it across the structure. And so that fundamental sort of raw definition will always work in constructing an influence line. But you all know that that we have a little bit of a shortcut for that, and that is the Müller-Breslau principle. Now I want to just sort of restate again the statement or the steps for the Müller-Breslau principle, because that's important to understand what we do today. We're going to apply the same process, but we're going to come to some different conclusions about rules and guidance for drawing influence lines for shear and moment. So I want to make sure that it's crystal clear what the process is, what we're following. Okay, so again, Müller-Breslau principle states that the deflected shape of a structure represents the influence line. If you take your quantity in question and you move it through a small displacement, and so what you're doing for the Müller-Breslau principle is you're identifying a response of interest. What are you drawing the influence line for? You drawing it for a support reaction of, shear and moment at a given point, whatever. Again, though, it's a point of interest. You're always keeping your eye fixed on a particular point of interest. You then remove from the structure the ability to resist that response. So if it's a support reaction, you remove that support reaction from the structure. If it's internal moment, you insert a hinge, and that'll become clear here in a bit. And then what you do is you move the structure through a deformation at that point. Then whatever the deflected shape is, that's the influence line. And we saw that in a variety of examples on Monday. Now this is the I want to recap the influence lines for reactions. I want to highlight a couple things just to make sure that we're on the same page. Okay, so influence lines for reactions. We had some rules that we had developed based on the Müller-Breslau principle and based on some general observations. So, for instance, and there's a fourth rule on here which isn't listed, but we'll identify that as well. So, the first point is that influence lines always equal 1 at the reaction and 0 at everywhere else. But I want to be clear, these rules are only for reactions. Okay, so these rules that you see here circled, we're going to come up with some different rules for shears and moments, and that I think that'll make sense. But just bear with me. Okay, so we're drawing influence lines for reactions, and so these 3 influence lines that you see here are all the influence lines for the 3 support reactions. And what you see when you observe these is that, let's say for the reaction, the influence line for the reaction at A, it equals 1 at A and 0 at the other supports. If you're talking about the influence line for the reaction at B, it equals 1 at B and 0 everywhere else. If you're talking about the influence line for the reaction at C, it equals 1 at C, 0 everywhere else. And likewise, if you sum up all the influence lines for A, B, and C, all of those corresponding associated values always equal 1. This plus this plus this equals 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 1, because of the equilibrium in the y direction. Sum of forces in the y direction has to be 0. And so if you're if the whole point of an influence line is placing a unit load downward, then all the reactions have to equal a unit load upward. That's why when you sum them up, they always equal 1. Okay, that's the first rule. Second rule, they're always linear for statically determinate structures. And that's because, you have a structure that's determinate. If you remove a response, you get an unstable structure. And so unstable structures don't really deform. They just freely displace. And so if it's linear before, it's going to be linear after. And then third is that the internal hinges serve to change the slope of the line. Now, I'll go ahead and tell you for shear and moment, these two are still true. They're always linear, and the internal hinges serve to change the slope. The first one isn't quite true for shear and moment. That'll become clear, but it's just something to keep in mind. Is everybody okay with drawing influence lines for reactions? You all just did a homework assignment on it, so if there's any questions, any conceptual things that we need to work out, I want to do that now because I don't want there to be any lingering confusion about what we do next, or when we start tackling our next topic. Everybody good so far? Okay, why was it 0 at the hinge on 820 for BY? Okay, hold on. Hold on. Give me a sec. I got to look at it. Okay, so let me pull up that problem. Give me 1 second, and I'll give you like a really quick overview on that. Let me see. I gotta pull up the image here. While I'm pulling this up, are there any other questions? Because I want to make sure this is clear. Okay, so let me go to this. Oops. Oh, I got to pull up the file here because I want this to be clear. I'm going to stop my share, and I'll answer this one. This is important. I want this to be clear. All right, let me share the application. All right. Okay, so this is the beam that we're talking about. Let me zoom in a little bit, or actually, let me take this and make it a little bigger. Okay, so you're saying why was it 0 at the hinge? Okay, here's why. All right, let me see if I can. Let's see if this becomes clear. Okay, so let's say you're drawing the influence line for the reaction at B. Okay, so you remove from the structure the ability to resist the reaction at B. So up here, this is what the structure looks like. This is what the structure looks like when it cannot resist a reaction at B. So it has that and that. Would you agree that that diagram is what the image looks like if it cannot resist the reaction at B? I've got the support at E, the support at G, and I've got the roller at B on, but I also have that internal hinge at D. Make sense? Okay, now what we're then going to do is we're going to take point B and we're going to lift up 1. So this is point B right here. We're going to take point B and we're going to lift it up 1. Okay, now look at this beam and think about it, mechanically. If I take this beam and lift it up, what's it going to look? What it's going to look like is this. Here's the beam right here. There's the reaction. There's this reaction. There's a hinge at D. So it's going to do this. Oh God, my art is horrible. Bear with me. it's just going to rotate about that hinge, okay? So the influence line for the reaction at B just goes up, down, and over. That's the influence line. Does that make sense? And so on your influence line, this point right here is 1.0, and you just use linear interpolation to find everything else. This is going to be 0.5, this is going to be 1.5, and so on and so forth. And that's your influence line. This is fine. I really want this to be clear, and I understand with influence lines, one of the easiest ways that you understand it is you just kind of have to go through it, you know. So no, I get that. Okay, let me close this. All right, is the audio and video coming through? My apologies, I accidentally closed the browser.
Yeah, I can hear and see you.
All right, thank you. Let me go back to the notes here. Okay, so sorry. Okay, so any other questions before I go on to shear and moment? Okay, now what I want to do with shear and moment is, first off, I'm going to show you what they look like, and then I'm going to show you why. Okay, so just as you can draw influence lines for the reactions, you can draw influence lines for internal responses. Now, one of the downsides or the drawbacks is that when you draw the influence line, you can only draw the influence line for a particular point, right? I can't draw a shear and moment influence line for the entire beam. I can draw a shear and moment influence line for a particular point on the beam. And so what you see here are plots showing the influence line for the shear at a point at section 1.1, or the moment at a particular point at section 1.1. And so that's probably one of the biggest drawbacks of influence lines, is that when you're looking at internal responses, you can only draw them for a single point. And so one question that I commonly get is, well, how many points are enough? Like, I mean, if I have a beam that I'm designing, I can only draw an influence line for a single point. How many points do I need to say that that's enough? Common practice in the field of bridge engineering is to draw them at every 10th point. So what that means is, if I have a bridge that's, I don't know, 50 foot long, I'll draw an influence line for the shear and moment at 5 foot from the support, and then 10 foot, and then 15, and then 20, 25, 30, 35, 40, 45, so on and so forth. And if by drawing 10th points, that's enough to generally capture the resulting moment and shear envelopes. Don't worry, we haven't talked about moment and shear envelopes. That's all next week. But that's close enough. Like, you could do 20th points or 100th points, but there's a point when you really don't increase your accuracy necessary for just designing the beam. And so 10th points is very, very common. In fact, if you see some bridge plans, like if you ever are able to get your hands on some bridge plans, sometimes the moments and shears are actually plotted on the plans. Like, sometimes they'll tabulate them, and you'll see that more often than not, they're split up into points. So that's just food for thought for later. Now, this is what the influence lines for shears and moments look like. I want to talk about how we get to this point. Like, how do you draw them? How do you use the Müller-Breslau principle? Well, In order to do that, before we get into drawing them, I want to recap some sign conventions because this is really, really important. Okay, so let's go back to our internal sign conventions. Okay, so remember, you have a beam, right? Let's do some drawing here. So you have a beam, right? And you got some boundary condition here, and there's loads here, there's a load here, there's a moment there, whatever, right? And then we say, okay, if you remember from when we did shear and moment diagrams, the first thing that we did was we learned how to determine internal response at a point. Like before we plotted the internal response, plotting the shear and moment diagram, we said, let's determine the shear and moments at a particular point. And so we would cut a section, and we would say, I'm going to cut a section, and I'm going to look either to the left or I'm going to look to the right. Okay, if let's say you decided you look to the left, right? So here's the beam, here's the support there, there's that load. I know my art is horrible. And here's the section. Here's the section that you cut. And so we cut a section, we look to the left. When you cut a section and you look to the left, you need to draw those internal shears and moments. We would always say that when you cut a section and look to the left, that downward shears are positive, and then moments acting in a counterclockwise fashion would be considered positive. Likewise, when you cut a section and you look to the right, you have the same magnitude, just the directions are flipped. Okay, everybody okay with that? I would hope by this point that's good. Now, what I want to do is I want to look at just the sign conventions as a whole. So let's take a look at the moments. I'm actually going to do moments first because I think it's a little easier to explain. So moments, if you look at a particular point and you look at the internal moments, see how they both sort of like rotate the section upwards, right? They're both sort of rotating the section internally. So they're both sort of rotating the section internally so that that rotation sort of points upwards. So when you look at the resulting influence line, you can see that you have an upward point, and that upward point is they're both sort of rotating that section upwards. When you look at the shear influence, the shear sign convention, let's take a look at the shear sign convention. Look at the left side. The left side points down, and the right side points up. So when you draw the influence line for shear at a particular point, here, let me go back to the influence line. Here's the influence line, and you can see, here's the point of interest, and then on the left side of that, we go down, and on the right side, we go up. So you can see how that's formulated. But I want to walk through this very carefully. I want to walk through how we construct this. So let me, and not just how we construct it, but how we get our associated values. So let's take a look at here at the board. So I have, where'd my mark? Okay. I have a pretty straightforward beam. I have a simply supported beam. And just to recap, let's make sure we're clear. This is the influence line for the vertical reaction at A. So it's 1 at A, it's 0 at B. And so we made some observations with that. We said, okay, whenever I'm drawing influence lines for reactions, I have a 1 at the support that I'm looking at and a 0 at all other supports. Let's see if we can come up with some similar stuff with shear and moment. We're going to do moment first. So let's draw the influence line. So influence line for internal moment at section 1-1. And I'm calling it section 1-1. You could call it point B or sorry, point C, whatever we call it, it's all the same. Okay. All right. So let's go back to the issue or the rules with the Müller-Breslau principles. So there's 3 steps. Okay. So step 1, identify a point of response. Well, we've already identified the point of response. We're drawing an influence line, internal moment right here. Okay, that's step 1. Step 2. We remove from the structure the ability to resist that response. Okay, so this is key. When we were dealing with reactions, we said we removed from the structure the ability to resist that reaction. So we basically just kicked the reaction off the beam. So we would kick that support off, and the beam would just rotate like that. Okay. Now what we're doing is we're removing from the structure the ability to resist moment, and particularly moment at this point. So I want you to ask yourself, here's this point on the beam. How do I remove from the structure the ability to resist moment right here? What do I do right here to remove the ability to resist moment? I'm asking the chat here on this one. So think, what can you add a hinge? Exactly right. That's exactly right. So if I put a hinge right here, I mean, what is the whole idea of a hinge? Remember, go back to when we were doing support reactions, right? When we did support reactions, when you have a hinge inside a beam at a particular point, that tells you that you know that the internal moment at that point is zero. Okay, so think about it like this. Now I have a beam with a hinge, right? I left my fancy little play at home. I brought it with me in case I had any questions on the homework. So let's say I have a beam here, and let's say it's connected, and now there's a hinge, right? So if I move that up and down, you know, that hinge is going to sort of act like that. So I've got two rigid segments. I've got a segment from here to here, and a segment from here to here, connected by a hinge. Okay, so that's my second step. You know, I identified a point of response, and I removed from the structure the ability to resist that response. So I said, I want the internal moment here, and to handle it, I'm going to put a hinge here. Now here's the tricky part. I need to take that structure and I need to move it through a unit displacement. That's what or unit deformation. That's what the Müller-Breslau principle states. I need to move that structure through unit deformation. Okay, so we're talking about moment. Okay, remember when we were dealing with work and energy, we said that, you know, one of the ways that you define energy is forces going through displacements. But another way that you define it is moments going through rotation. So there's two different expressions that we can use for work. And so what I'm really going to do is, instead of moving this point through a unit displacement, what I'm really doing is I'm moving it through a unit rotation. And so let me explain how I'm going to do that. Okay, so here is here's my influence line. I've got a hinge here. I propose what I'm going to do is I'm going to draw the influence line so that it looks something like this. Here's where the hinge is. It's going to go down like that. Now, the $64,000 question is, well, that's great, Dr. Mike, but how high did you move it? Okay, it's not really a matter. I mean, I can determine how high I moved it, don't get me wrong, but I'm not really so much interested in developing the rules based on how high I moved it. Here's my point. Okay, I've got these two rigid segments. I propose that each of these segments are going to be at a different slope. So we'll call this slope 1, we'll call this slope 2. Okay, so this is a slope, this is a slope. Remember, we said that we're moving it through unit rotation. Well, remember when we were talking about deflections, we said that in our world, slopes and rotations are sort of synonymous. So I propose that what we're doing is we're figuring this out such that slope 1 plus slope 2 equals 1. That's the unit displacement that we do for the internal moment at a particular point. Now, I've got some figures here that describe this a little better than I can draw. So let's go to here. All right, so this is a little clearer. So we have the influence lines for moments. What we're going to do is we remove from the structure the ability to resist moments, so we put an internal hinge at the point of interest. We then move a structure through a unit rotation. So what that effectively means is that the total slope of those two rotated portions must be 1. Now, how do you compute slope? Okay, so let's take this line right here. Okay, that diagonal line that I highlighted. What is the slope of that line? The rise, whatever that height is, over the run. Okay, and what about this line? What's the slope of that line right there? Well, it's the rise over the run. Okay, so I know my drawings are a little sloppy there, but the idea is that the total slope must equal 1. So now we have a rule that we can use to determine the height of that peak. And if I know the height of that peak, and I know that if I got the height of the peak, I can use linear interpolation to figure everything out, or figure everything else out. Now, there's one thing I did kind of gloss over that I think is really, really important that I want to spend some time on, and that's what's going on right here and right here. Okay, I just sort of said that the influence lines were going to be 0 at the supports, but let's talk about that. Let's see if that makes sense. Okay, let's go back to our basic definition of an influence line. What is the basic definition? We take a unit load like this, 1 kip load, and we move it across the structure, right? So let me ask you a question. If I take the load right here and put it right over that support, okay, we know that the reaction is 1 at that support and it's 0 at all other supports. That's easy, okay? But now let's ask a different question. When I put a load at a reaction, what is the internal shear in the beam? What is the internal moment in the beam? More specifically, what's the internal response in a structure when the load is on the reaction? The answer is 0. There is no internal response in the structure. Like if I have a beam and I put a kit, 1 load right there over the support, I'm going to be completely loading that support and the structure is not going to be seeing anything. So one of the general rules that we can develop when we're drawing moment influence lines is that whenever you're drawing an influence line for an internal shear or an internal moment, it's got to be 0 at the reactions, because if I put the load at the reaction, I'm not going to generate any internal response in the structure. Does that make sense? I want to see if there's any questions about that, because now what I'm going to do is I'm going to talk about shear. And don't worry, we got some examples on this. We'll get some numbers on this.
I just have a quick question here.
Yes.
So, on the your example on the far bottom here, where we had determined our lengths and our heights.
Mm-hmm.
So we don't know. We'll have to determine what the lengths are for each respective slope. That'd be an x value of the total length, or to the hinge. Or...
Well, here's what I'm getting at. So let's take like an example problem, right? Let's just take this problem and let's just sort of work through it. When I draw the influence line, let's say I'm drawing the influence line for the moment at B, I'm going to put a hinge at B, and then it's going to, sort of go up and something like that. Sorry, my pen's getting away from me. So here's the hinge, and then it's going to peak up, something like that. I've already got my lengths right there. The L1 and the L2 is already figured out from the beam because I know where I'm drawing the moment. The issue is not the L1 and the L2, as you'll see when we go through the example. The issue is figuring out how high that is. When would a moment influence line ever go into the negative? You're going to see that here in a little bit. You're going to have examples on that actually in 2 or 3 minutes. Well, actually, once I get through the shear influence line, you will see. The easiest thing will be to go through that when we do the examples. Let me start talking about. So I've talked about the moment influence lines. Let me talk about the shear influence lines. I think the shear influence lines are. I don't want to say a little trickier, but it's actually, I think, easier to understand how to draw shear influence lines once you learn how to draw moment influence lines. So let's go back to our basic theme here, and let's see if we can draw the influence line for internal shear at 1, 1. Okay, so let's draw the influence line for the internal shear at section 1, 1. Okay, So a couple things to observe. We observed that whatever our influence line was for moment, it had to be 0 at the supports, okay? We're going to get the same response here. Again, if I, think about it like this. Here's my unit load. This marker is my unit load, and it's moving across the structure. Well, if I put the load right here at A, I get a full reaction at A, and I don't get any response anywhere else. I mean, just think about it. If you have a beam, sitting right here, so here's my beam, and I put the load directly on the support, how much internal forces or responses is going on in the beam? Nothing, right? If I've got the beam and I put the load directly on the support, or like if I put it, right here, the beam doesn't see anything. So whenever you're drawing an influence line for an internal response, it should be 0 at the supports, okay? Now, for drawing the internal shear, there's a couple things I want to point out. So first off, whenever we draw the influence line for internal shear, it should go down on the left side and right on the, or down on the left and right on the up. So here's my, draw this sort of guideline here so that I've got something to go off of. I propose that, here's my influence line. It should be negative, somewhere over here, and it should be positive over here. But that doesn't, that makes sense from a sign convention standpoint, but it doesn't really that doesn't really give me the full picture. Let me give you the full picture. So when you go back to the rules for the Müller-Breslau principle, we remove from the structure the ability to resist shear, okay? Now what that means is we install what's called a shear release. Now, this is the first time we've ever really dealt with a shear release. Here's the long and short of it, because you don't really need to get super marred up in the nitty-gritty details. All you need to recognize is that a shear release does just that. It releases shear, but it doesn't release anything else, okay? So just like a moment release can releases moment, but you can still take a hinge section and yank on it. You can still take a hinge section and shear on it. Like, here's my door, right? Here's the door. The door hinge freely allows rotation, but I can take this door and I can yank on it. I can yank on it axially, and it still resists it. I can take it and shear it, and it's just fine. It's only the rotation that I'm releasing. Same thing with a shear release. I'm only releasing the shear, okay? So because I'm only releasing the shear, what that means is I'm not releasing the moment. So I have to draw this influence line in such a fashion that this line and this line both have the same slope. So this line has a slope, this line has a slope. Those slopes are identical, okay? Now, that's fact number one. What's the other fact you need to know? Let me ask you this, and this is probably one that you could guess, okay? So here's the influence line for shear at 1, 1. That's the plot. That's what it looks like. What I'm asking what I'm asking chat is this. I know these lines have to have the same slope, but help me out. What do you think that distance is right there? So when you look at a shear influence line, there's a jump, right? There's a it goes down, and then there's a jump, and it goes over. How much do you think that total jump is? I'm just curious. 1, exactly right. So to give you some numbers, let's say that this was 3/4. This would be minus 1/4. If this was 3/5, this would be minus 2/5, so that the total jump equals 1. That's basically it for shear. So let me go back to the slide here to kind of show you what's going on. So when you're drawing a shear influence line, again, what you do is you institute a shear release, and what that shear release does is it allows shear translation, but nothing else. So the two lines have to have the same slope. So that total displacement has to equal 1, okay? And then all we basically do is we say, okay, let me use some pens here. We say that this line and this line have to have the same slope. So H1 over L1, H2 over L2. But those two slopes are identical. But whatever the H1 is and the H2 is, they have to add up to equal 1. So what we can do is we can come up with a really simple expression to solve for the heights, and then we're rocking and rolling. So I think that the easiest way to demonstrate this is to go through some examples. But just to summarize, the expression for moment is that total slope has to equal 1, and the expression for shear is that the total jump has to equal 1, and those two lines are at the same slope. So for shear and moment influence lines, the influence lines will always equal 0 at the reaction. If the unit load is over the reaction, the beam is not going to experience any load. They are still linear. The internal hinges, again, serve to change the slope of the line. So with that, let's just sort of get into some examples, because I think that's the easiest way to demonstrate how this stuff works. So let me pull my notes up. Okay, so let me go back. Let's go to problem 1. Okay, so let's recap. This is what we did last time. We drew the influence line for the reactions for this beam. And one of the things that was brought up on Monday was, that point B. Does that point B really matter? No, that point beam didn't really matter for the purposes of drawing support reactions. It was just a point on the structure. Now what I want to do is I want to go back to this beam. I want to draw the influence lines for shear and for moment. Okay, so let's take shear first. Okay, so let's sort of see if we can reason through the shear influence line. Okay, so a couple things about the shear influence line. Number 1, the shear influence line has to be 0 right here, and it's got to be 0 right here. Okay, that's got to be the case. If I put a load directly over point A, or I put a load directly over point B, I get no internal response in the beam anywhere. Okay, that's just the facts there. Okay, so that's point 1. Here's point 2. What I'm going to do for the shear release is I'm going to translate this so that the left side goes down, the right side goes up. And I have to do it in such a way that the two lines have the same slope. So here's what I propose that the influence line looks like. Let me get my line tool out. I propose that it probably looks something like, I don't know, like that. Oh, sorry, I didn't mean to do that. So it probably looks something like that. And then for the other side, probably looks something like that. And that right there, that's the influence line. Okay, now that's what the influence line looks like in principle, but what we haven't figured out are the values. Okay, so in order to figure out the values, what we need to do is we need to start where that release is. Okay, we need to start where that release is, and basically what we're trying to figure out, let me get another color here. What we're trying to figure out is this height here, which we'll call H1, and this height here, which we'll call H2. So how do I do that? Well, I propose that the slope of those two lines are identical. So H1 is, we're talking about this line here. What's the slope of that line? H1 is to 20, right? Rise over run, as H2 is to 10. Okay, that's pretty easy, right? The other thing that I propose is that H1 plus H2 has to equal 1. Okay, so from here, this should be a pretty simple puzzle to solve, right? If I take this expression here and solve it, what do I got? I got H1 is 20 over 10 H2, which is 2H2, right? And so I can say, I can take that, plug it into here. Instead of H1, so we have H1 plus H2 equals 1. And instead of H1, I'll just put 2H2. 2H2 plus H2, 3H2 equals 1. H2 is 1/3. And so I propose this is 1/3, that 2/3, or I guess more specific, negative 2/3. Now, let me move this down a bit. Okay. Before I move on, any questions? Did I go through that too fast? Tell you what, I'm curious to see what you all answer here. What is that? What's that value? Negative 1/3. There you go. Exactly right. And boom, that's it. That's the influence line for the shear at B. Now, Mr. Enod had a question about moment influence lines. Let's see if we can address that. So, moment influence line. Again, let's reason through this. We're going to have a 0 right here, and we're going to have a 0 right there. If I put the load at A or I put the load at C, I'm not going to get any internal response in the beam. Okay? Now, moment influence line. I put a hinge at B and I move it through a unit rotation. So let's go back to the sort of the question that maybe Mr. Romans asked. You know, if I put a hinge, so I'm putting a hinge right there at point B, okay? I'm fixing the beam there, fixing the beam there. So what does it look like if I take point B and lift it up some, okay? Well, from point A to point B, it's going to do, hold on. From point A to point B, it's going to do something like that. And then from point B to point C, and then following on, we're going to anchor that here, and it's going to go negative. This is the influence line for the moment at B. So to answer Mr. Enod's question, can influence lines for moment go negative? Yes, they can. Think about the physics here. Imagine if I have a beam and I put a load right there. What happens is, you know, the beam kind of wants to deflect like this. It kind of wants to go frowny face. So here, that's negative moment. Whereas if I have the beam and I put the load right here, it kind of wants to smile, and that's positive moment. Hence why we're getting positive values here, negative values there. Does that make sense? Now, okay, now what we have not done is we have not figured out any values on the moment influence line. Let's see if we can figure those out. All right. Ultimately, what we're trying to figure out is that height, okay, because we don't know what that is yet. But I propose that whatever that height is, the slope of this line and the slope of this line have to equal 1. Okay, so what is the slope of the line on the left? It's rise over run. What about the slope of the line on the right? Rise over run. H over 20 plus H over 10 has to equal 1. This one's a lot easier. So H over 20 plus H over 10, we'll call that 2H over 20. This is going back to like arithmetic, equals 1. And so 1H over 20 plus 2H over 20 is 3H over 20. is 1. H is 20/3. It's a good point. Okay, so here's the thing, and this is probably one of the habits that I really want to break. An influence line is not a moment diagram. That's the thing that you have to sort of break your conception of. An influence line is not a moment diagram. I'm actually going to say it one more time. An influence line is not a moment diagram. I know they look like moment diagrams and they look like shear diagrams, but they're not. They're the internal response as the load moves. The hinge and the shear release and whatnot, those are sort of mathematical tricks where you draw those influence lines, but again, they're not moment diagrams, and that's sort of the kicker. What I'm saying is this is the internal moment B as the load moves across the structure. Okay. Now I'm just curious, and then I really want to try and attack the second problem here. What is, oh, come on. What do you think that point is right there? Let's see if anybody's paying attention. What's that point? There you go, negative 6.67. That's exactly right. And that's it. Like, in terms of constructing the influence line, that's it. There's really nothing to it. Let me show you the next problem, because I know the next problem looks scarier, but it really isn't. That's the whole point. So here's this beam. And I know it looks like a mess, okay? It really isn't. Okay, let me scroll down a bit. Let's look at drawing the shear and moment influence lines for this beam, okay? So let's move this down a little bit, give us some space. So we'll say the influence line for the shear at that section and the influence line for the moment at this section. Again, this is a really, really simple process. Let's take moment first. Moment, I think, is a little easier. So you better have a 0 here, better have a 0 here, better have a 0 here. Let me lower that a bit. 0. Okay, so watch this. Let's take moment. We're going to insert a hinge right there at section 1. Let me ask you a question. How many segments, if I put a hinge at section 1, how many segments am I breaking this beam up into? How many different rigid segments are there? 3. Okay, so if there are 3 rigid segments, there's going to be 3 segments on the influence line. I'm going to take that point and move it up. So what's that going to look like? Well, I'm going to go up here. That hinge is going to cause a change in direction, but it's got to go through 0 right there. Then I've got a hinge. Goes there. Boom. There's the influence line for the moment at section 1. It's that simple. Okay? That simple. How I'll talk about doing the values. How do I get the values? How do I get this value right there? Well, the height is to 14 plus the height is to 6. That's the total slope. That has to equal 1. Simple. All right. Once I've got that, use linear interpolation, use slope ratio, get that. So I'll go ahead and give you some answers on that. X is to 14 plus X is to 6 equals 1. This comes out to be H is 4.2. So that is 4.2. And if you know this, well, what about that? Well, 4.2 is to say 14 as whatever that height is to 8. negative 2.4. Really not that difficult, okay? For the shear release, same process, okay? Same process. I know we're running out of time, so I'll do this one quick. How do we do with the shear? We institute shear release. Left side goes down, right side goes up. Has to be anchored at 0. And again, just like Mr. Enoch mentioned, 3 rigid segments. 3 rigid segments. So what does our influence line look like? Oh, come on. Here we go. We go up on the right. Oh. On the left, we go down, and we go down such that those 2 lines are at the same slope. Go up there. That's the influence line for the shear at that point. It's that simple. I'll go ahead and give you some values in case you're interested. And you ought to see if you can chug these out on your own. But this one ends up being 0.3. This one ends up being 0.7, but it's negative. And this one ends up being 0.4. You ought to see if you can reason through those. Again, your attention should first be focused to the release to see if you could determine those independent ratios. And once you figure that out, you can figure this one out just by using slope ratios. And that's it. That's the long and short of it. Any questions? I know we went through that part kind of fast, but if there's any questions, I can go through them. All right, I'm going to leave y'all to it. What I'll probably do is this. I might post a video on Teams just to, in case anybody has some questions. I might go through some of the math on the slope differences a little bit. I don't think it's that difficult, but just to make sure that it's covered, I'll post that there. And then what we're going to do on Friday is look at fixed supports, because every rule we've talked about with fixed supports remains true. We just have to do a little bit more investigation. That's all I have, everybody. I will see you all on Friday.